All right, books open to page 188. We've been working on functions lately. We've talked about two types of variation in our functions, and those two types of variation are, Mackie? Direct and inverse variation. What's the form for direct variation, Kendall?
Y equals kx.
And remember, we got to find out what the k is to really truly know the variation relationship. And then the inverse variation, Michael?
X, Y equals K.
This is, to me, the easiest form to use. What's the other form you might see on a quiz or test, though? Genesis? This is the form I gave you. It's not what's in your textbook, but it's easier to use than what's in your book.
K over XY.
Y equals k over x. So here, remember, y is a multiple of x, k times the x. Here it's a multiple of the reciprocal, k over x. Or you could say k times 1 over x, a multiple of the reciprocal. Here it's just a multiple of the x. And that's what we were working on in the first couple of problems. Number 15 from the homework, it tells you it's direct variation, though you probably should have figured that out anyway as you were working, because every time, what's the relationship between the x value and the y value? How every time do you find the y value? Audrey?
Multiply by a half.
Good, you just take half of the x, right? Cut the x in half, boom, there's your y value. Half of -2, -1, of course, half is 0, 0, and so forth. So what's the, if that's the constant of variation, what's the equation for 15? You said it's direct variation, and you said the k was what?
1/2.
All right, so what's the equation?
Y equals a half x.
There we go, y equals a half x. Pretty straightforward. Looking at the next problem, this was now a word problem. It says a grocery store owner knows if he puts milk on sale, the store will get more customers, indirect variation. The store gets 30 more customers than when the milk's price is reduced by 10 cents. Now, I'll be honest. If milk goes on sale for 10 cents cheaper, I wouldn't notice. But how many of you, your mom would notice if the sale went 10 cents cheaper? Okay, yeah, so y'all know what they're talking about, and that's not me necessarily, but I've seen it. Like when Aldi first came to Columbus. I mean, you remember your moms when my wife and I were even that. We're like, eggs are only 79 cents a dozen. Found them on sale for 6. Stock up. Limit 4 per customer. Let's get 4. Anyway, I tell you. But like $1.29 at the Walmart, 69 cents. Yeah, I get twice as much. Anyway, not quite, but it's close. All right, round numbers. All right, anyway, so 30 more customers if you reduce the price by 10 cents. So if you reduce the price by $1, that should be a lot more customers. When we go to set this up, how might we rewrite this formula instead of using x and y, maybe using some other variables?
C equals KP.
C equals KP, where P represents the drop in price and C represents the customers they would get. So we said that a 10-cent price drop will result in 30 extra customers, correct? What is K equal to then? 300. So that's the constant of variation. So then, really, my equation is?
C equals 300x.
Or P, right? You went with P before, so C equals 300P, right? Number of customers who are going to come in is equal to 300 times the amount of price drop. So, if the price drop is $1, what's the customer count going to be then? 300. How many had the 300 customers if they lower the price by $1? Questions on this? We vaguely remember doing this at some point in our lives, like last week. All right, if you're watching on YouTube, it might have been 2 lessons ago, but for them it was, 5 days ago. All right, let's take a look at number 19. And here we have inverse variation. Again, you should be able to tell by looking at it. Yeah, that's definitely inverse variation. Because as the y values seem to be getting smaller, the x's seem to be getting larger. But what's the constant value here, Abby?
7.
7, because if we multiply the x and y, we always get 7. So that's my constant. So we could say the equation is?
XY equals 7.
Or if we were to go with the other format, we could say?
Y equals 7 over x.
Good. Either of those would have been sufficient. How many had that answer? 4 number, whatever it was. You had that 7 as the constant. Questions? Now let's take a look at the problem here. It says the town noticed that the more police officers they employed, the fewer crimes were committed. When they employed 25 officers, there were 100 crimes. Determine how many crimes would be committed if the town employed 125 officers. Defund the police? What? Anyway, we're not getting into politics right now. All right, so what equation could we set up here, Maddie? OC equals K, where O represents officers and C represents crimes. Okay, so they said 25 officers, 100 crimes committed. I'm not sure if that's like annually, monthly, daily? Anyway, sounds like Columbus. All right, and so what is the K value then? So really, what's my formula? There we go. OC equals 2,500. Or you could say O equals 2,500 over C. That would be fine as well, I suppose. Then it says, well, if there's 125 officers, how many crimes can they expect to be committed during whatever period of time they're talking about? 20 crimes. How many had 20 crimes on 21? Questions on these? All right, number 23 on 25 and 27, they were asking you to determine whether or not the information given represented a function or not. Number 23, what was your verdict that you came up with here, Kendall?
No function.
No function, and why did you say that?
Because the x's were different.
Well, remember, if all the x's are different, that means that x value doesn't get repeated. That's the key to a function. An x value can't be used more than once to get different results, right? So, for instance, graphically, because I think that's the easier way to think of it. For instance, let me skip to 25 real quick. 25, yes or no function?
Function?
It is a function because remember that vertical line never crosses the graph more than once. That means that no x value has more than one y value. But remember, if we saw something like that, that would be not a function because this one x value has 1, 2, 3 different y values, correct? So a repeated x with multiple y's is what makes not a function. Well, here, every x is different, no repeated y, and it really doesn't matter if y's are repeated, but no repeated x's, that actually would make it a function. Does that make sense now? All right, number 25, we already said yes, it is a function, it passes the vertical line test. What about number 27? How would we determine whether or not that is a function, Michael?
I forgot, but I put yes.
All right, how do we determine it though, Genesis?
I forgot, but I put yes.
It's like it worked for Michael, got him out of it. All right. Who remembers how to tell whether or not it's a function? Audrey sort of raised her hand, like raised a finger. Solve for the y, and if you get a, if you just get one single thing, it's a function. But if you get a positive, negative, that's usually the indicator. You get some positive, negative, that's going to clue you in, can't be a function. So on number 27, we get the y by itself. Back to Michael, what does it look like?
12 minus x.
12 minus x. Well, I don't get a positive, negative there. Every x I would plug in would give me a different y every time. I'm not worried about any repeated values there. So number 27, yes, it is a function, but that's y. It is a function. Questions on those odd problems? Questions? All right, turn back to page 187. And let's also take a look at what we were working on last lesson. That was using or evaluating function notation. Remember I said f of x is just another way to write the letter y. Instead of using y equals, we could rename the y a function of x. That is, it's the dependent variable. It depends on x. We'll call it a function of x. And by plugging in f of some number, that tells me what to plug in for the x. So they gave us the function in number 1, f of x equals x cubed plus 15x squared plus 3x minus 10, and it said to evaluate f of negative 3. What that means is all 3 places that I see an x, I gotta plug in a negative 3. So Genesis, when I cube a negative 3, I'm gonna get,
Negative 27.
when I square a negative 3, that's gonna give me, square a negative 3, get a positive 9 times 15, 135. And then of course, negative 3 times this 3, negative 9 minus 10. We evaluate and we end up with
89.
positive 89 is correct. How many got the same answer for number 1? Questions on number 1? Sure, we're careful with our signs there. Again, you can use your calculator to do it if you need to. Just be careful with signs. Looking at number 3, they didn't use f of x, they used h of x. That's fine, it means the same thing. It's just a different function of x. And we've got 2x plus 10 over negative x squared plus 42. And he wanted us to evaluate h of 5. Well, again, when it says h of 5, that means we need to do what, Brandon? Right, so in the numerator, I end up with a 20, 10 plus 10. In the denominator, I end up with, well, careful, it's negative x squared. It's only the x that's being squared, not the negative. So it's going to be a 5 squared is 25, negative 25, positive 42 should have given us 17. And we can't reduce it, so let's leave 20/17. How many have the same answer here, 20/17? How many did what Brandon did and you forgot the negative wasn't being squared? It's not negative x squared, so I'm going to make this a negative 5 squared. It's just negative x squared. You had the same thing. You had 20/67. Okay, if you did that, questions on this. All right. And then on the last one, we had f of w is equal to the square root of negative 6w squared plus 30. This is kind of the same idea as what we just saw. What is being squared here, class? The w, not the negative 6. So we're going to have to square whatever w value they give us, then multiply the negative 6, then add the 30. And of course, they ask for f of 2. And so, Abby, when we plug into 2, we're going to start by squaring it. 4, and then multiply by the negative 6.
Negative 24.
Plus the 30.
6.
So we end up with just the square root of 6. Same thing here. We square the x first, then multiply by the negative 1, if you will. That's in front of the x. Does that make sense? All right? How many got the square root of 6 on number 5? By the way, can you take the square root of a negative with real numbers, class? No. In fact, the square root of a negative is the definition of an imaginary number, right? So here, what if they've given us a 3? What's 3 squared? 9 times negative 6. Negative 54. You realize they couldn't have given us a 3. Not in work with real numbers, which is what functions deal with. They deal with real values. And so there was a limitation on what we were allowed to plug in there. I want to bring that thought to fruition in your notes. I'm going to talk about a couple of terms. First term I want you to write in your notes is the term domain. Domain. Depending on your calculator, some of you may occasionally get the error message, domain error, on your calculator, depending on what you plug in. The TI-30XA just says error. Some calculators say syntax error. Others will say domain error. Syntax error usually means you entered something wrong. Domain error, what's that talking about? Write this definition down for domain, if you would. Domain refers to the set of all values that may be entered for the independent variable. The set of all values that may be entered for the independent variable. The set of all values that may be entered for the independent variable. Practically speaking, this refers to x values that you're allowed to plug in. For instance, I made the point you can't plug in a 3 right here. That causes a problem. Not 4, 5, 6, 7, 8, 9, none of those. 2's okay. What's another number I can plug in for W? 1. Another? 0. Any others? Negative 1 would be okay, wouldn't it? Because you square it, it gives you a positive 1 times negative 6. That's negative 6. That's still positive, though. Negative 2, okay? Negative 3? No. Really, you can do a little bit bigger than 2, though, right? Because 2 got you to the square root of 6. But if you plugged in the square root of 5, well, obviously you square that, you square square root class, you get the radicand. See, the square root of 5 is the biggest number we can plug in there? Similarly, negative square root of 5 would be the smallest value. As long as we stay between negative square root of 5, which is like, what, 2.2, something like that, and positive square root of 5, or excuse me, negative 2.2, and square root of 5, which is like positive 2.2-ish, we're okay. Anything bigger than the square root of 5, anything smaller than the square root of negative 5, just won't work in this function. There's a very narrow domain of values we're allowed to use. Does that make sense? Similarly over here, now again, this is being kind of a random number, but the square root of 42, whatever that is, it's like, what, 6.5-ish, something like that? Well, if you take the square root of 42 and square it, of course, class, that gives you 42, but it's negative, isn't it? So negative 42 plus 42 would give us, but remember we said you can't have a 0 denominator. As we worked through our rational expressions back in section 1.7, we said denominator can never equal 0. You can't plug in a square root of 42. Now, the good news is that's not a number most of you would have thought of anyway, but anything else is fine, but you can't plug it in. There's a limitation on the domain in both of those. Does that make sense? There are certain values you're not allowed to plug in. Make sense? It's not a restriction on free speech or anything. Mathematically, you cannot plug those values in. There's also limitations sometimes, though, on what you'll get out of a function. We call this the range. That's a lowercase r. I'm just horrible at them in cursive. The range refers to the set of all values that may be obtained for the dependent variable. The range refers to the set of all values that may be obtained for the dependent variable. The range, the set of all values that may be obtained for the dependent variable. Well, typically that means these are going to be our f of x values. So all the f of x values that we're able to get out from the function. For instance, this square root has an understood positive in front of it. What that means is you're never going to get a negative answer here. Even when you plug in the negative square root of 5, the answer you get will always be positive. Make sense? But if there had been a negative in front, then all the answers you'll ever get out of it will always be negative. Does that also make sense? Right? If I had something like f of x is equal to x squared plus 3, well, no matter what you square class, you're always going to get a positive. And you're going to add 3 to that, which would make it even more positive. If you can imagine infinity and then add 3 more. But it doesn't matter what it is that you plug in, you're always going to get at least a 3, right? If you plugged in a 0. Anything bigger than 0 just makes the number get bigger and bigger and bigger until eventually you get theoretically to infinity. That's all you can get out of that function. Make sense? You can plug in whatever you want. There's no limitation on the domain as far as what you plug in. But whatever you plug in, you're only ever going to get out positive values. That's what you get out. That's your range. Does that make sense? So what you plug in, class, the group of all the numbers you're allowed to plug in is called the domain, and the group of all numbers you'll ever get out of a function that is called the range. Okay? So domain practically x values, and range y values, or f of x values. Make sense? Now, write this down if you would, and put a star next to this. You're going to assume that the range is negative infinity to positive infinity. Actually, you're going to assume both domain and range. I think I might have just said range. You're going to assume that both domain and range are positive to negative infinity, or all real numbers. I think I've introduced you to that symbol earlier in the year, correct? Okay? We're going to assume that this is the domain and that this is the range unless there's a limiting trait present. Something that would limit you from being able to plug in whatever you want. So as a general rule, you just look at any random function, you're going to assume I can plug in anything. And for the range, you're going to assume I can get out anything unless there's a specific trait, something about the function that tells you, wait, no, I'm not going to be able to get out anything, or I'm not going to be able to plug in whatever I want. There are certain traits, and there are 5 of them we're going to get in our notes. So 5 limiting traits to a function. I want you to get that down as kind of a continuation of this, but you might call it the next section in your notes. 5 limiting traits. That will cause our functions not to have all real number domain, all real number range. The first one, well, for instance, let me show you something real quick before I get into the limiting traits, okay? If I just said f of x equals 3x minus 5, there's no reason I can't plug in negative 72 for x. I mean, I get out a really small negative, like negative, like 217 or something, or 221 or something weird like that, right? But I can still get out a value, right? There's no reason I couldn't plug in negative 70. I could plug in a 5,392. I don't want to have to do the math on it. I can plug in whatever I want, right? There's nothing about that that tells me, ooh, you better not plug that in because, like for instance, the fraction, you can't have a denominator 0. Like that radical, you can't take the square roots of negatives. And it's not like, well, remember that square thingy? Like if this had a square, okay, well that's going to change the game a little bit because now this little piece can only ever be positive, right? So if this has to be positive and you take 5 away from a positive, the smallest number you could get would be what? -5, right? Take 5 from a positive. Well, let's suppose 0 is our smallest positive. The lowest number I'll ever get out would be -5. It didn't even have that, right? There's no reason I can't get out this. So for this, I'd say that my domain is all real numbers, and then my range would likewise be all real numbers. If this had been a cube, well, so what? You cube it, if it's positive, it stays positive. You cube it, if it's negative, it stays negative. I can still put in anything, you still get out anything. Does that make sense? One limiting trait, though, that will keep you from getting that is what's called a constant function. A constant function. A constant function is going to limit what you're able to get out of your function. And it's kind of stupid easy, right? This is an example. F of x equals 4. F of x equals 4. Now let's suppose I said, well, let's evaluate the function. Let's say, well, what is f of 0? So everywhere we see an x class, we plug in a 0. Thoughts? There's no x's. So I get 4. And if I plug in f of 1, well, I plug in a 1 for the x that isn't there, so that means I don't have to plug in anything, and I get 4. You get the idea? If you wanted to think of it this way, think of y equals 4 or y equals 0x plus 4. The x is a non-factor. It doesn't even matter, right? It's just y equals 4. Basically, no matter what you plug in, you've got this y-intercept of 4 and a slope of 0. 0, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4. You're always going to get a 4, right? Now, is there any limit to what I'm allowed to plug in? Well, considering there's nowhere to plug it in, I guess I can plug in anything I want, right? You know? So for this, for a constant function, we'll say that the domain is all real numbers. But the range is simply going to be, in this specific instance, 4 to 4. In brackets. That one number. Can't be nothing else. That's all you'll ever get out of it. Okay? Make sense? Kind of like those, maybe when you, ladies, guys, hopefully, have those little dolls or whatever, and maybe you push a button or squeeze their wrist or something and they talk, but they only ever say the one thing over and over again. Those were boring dolls, right? They made dolls that talk like lots of different phrases, but if it only says the same thing over and over again, doesn't matter what you do, only one answer. That's kind of like that doll. It's just 4, 4. No matter what you play it for, that's always the answer, 4, right? And so that's a constant function, where the y value, or the f of x, is equal to a constant. No variable at all. And a constant function, you plug in whatever you want because there's nowhere to put it, and you're only ever going to get out whatever that value is. Make sense? We don't see functions like that very often, but that is a limiting trait. Having a constant function be a limiting trait. Another limiting trait is an absolute value function. Absolute value is going to limit our functions and what we get out. For instance, write this down. F of x is equal to the absolute value of x plus 2 plus 3. F of x is equal to the absolute value of x plus 2 plus 3. Now, the key to absolute value is it can only spit out what kind of values? Positives, right? So no matter what you plug in, this here is guaranteed to be positive. In other words, it's guaranteed to be between 0 and infinity. Now, how can I get a 0 in here? No, if I plug in a 0, I get a 2. How do I get a 0 in there? -2. If I happen to choose a -2, that'll make this 0, right? Anything else will end up giving me something bigger than 0, right? -1, for instance, would give me a 1 as its absolute value. A -3 would still give me a 1 by the time you take the absolute value, right? So this has to be between 0 and infinity. And then I'm going to add 3 to that. Well, you know what kind of values we're going to get out? Values between 3 and infinity. Does that make sense? Well, what if this had been a negative right there? Well, now what kind of values is this thing going to spit out? Now, if you account for the sign, now it'll spit out values that are negative. As small as negative infinity, but only as big as 0, right? And then you have to add 3 to that. Well, what's that going to do? Well, it's going to take from -3 to 0, it's going to add 3. So it's going to go negative infinity up to 3. Does that make sense? As your range. But you can still plug in whatever you want, right? It's just what is the function going to do to whatever you want it to plug in. Make sense? So for an absolute value, your domain is still all real numbers, but your range is either from, for instance, in this case, 3 to infinity, or negative infinity to 3. Notice that the 3 refers to the value that is added or subtracted, in this case added, to the function. How do you determine whether it's 3 and up or 3 down? It all hinges on whether it's positive or negative. So a positive takes you up to infinity, a negative would take you down to negative infinity. Make sense? Again, these are things we'll memorize, but if you can understand how the math works, you don't have to so much memorize, it's just kind of figure out patterns, and that's what I'm shooting for. Questions on these first two traits? All right, the next trait is something we've already looked at. It's that squared thing. Because remember, like absolute value, squared values have to be, class, positives. So we'll say a quadratic feature, a quadratic trait, the x squared, if you will, is the next limiting trait in a function. For instance, if I said f of x is equal to x squared negative 8x positive 14, or something weird like that. Well, again, the quadratic, because of this x squared, whatever I plug in here has to be positive. But because of this, you understand you could get some negative values, couldn't you? For instance, you plug in, oh goodness, let's suppose we plugged in a, well, I don't know, this would be close. This would be close to getting some negatives. Maybe a 2 would be close. Right, because 2 squared 4 plus the 4 is 18, but negative 8 times x, that's going to be negative 60. It's going to be pretty close to 0. So you're not guaranteed positives necessarily from a quadratic, but here's what a quadratic will always give you. When you graph a quadratic, you're always going to get this shape called a parabola. And I want you to write that term in your notes. We're going to study parabolas in a lot of depth later. For now, you just need to know the term parabola. And a parabola is this U-shaped thing. All quadratics will be graphed as parabolas. What you need to know about a parabola specifically is the vertex point. You need to know that the lowest point of a parabola is called the vertex. Well, if you picture this, you notice the parabola just keeps spreading wider and wider and wider and wider. In theory, if you had enough graph paper, your parabola would just keep going wide enough, it would end up extending all the way to infinity, all the way to negative infinity. Does that make sense? As it's going up, 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 up to infinity. Make sense? So the domain on a quadratic function, you can still plug in whatever you want. Those x values are whatever. But the y or the f of x has a specific starting point, and it's the vertex. The vertex is the low point, and it can go from there upward. Now, again, later you'll learn how to find the vertex yourself. For now, you'll have to be given the vertex on problems like these. So let's just suppose for this function, I actually copied it wrong. Let's try x squared plus 8x plus 14. The vertex is going to be at the point negative 4 to negative 2. That's the vertex. Okay, then that means that the range is going to go from this y value, negative 2, this f of x value, this ordinate, all the way up to infinity. And there's my range. You'll have to have the vertex of the parabola in order to actually find it for now. Again, later on, after the after the next test, teach you how to find the vertex yourself, and then you'll have to do the whole thing. But for now, negative 2 to infinity. But a parabola could go down. Well, in that case, it's still going to spread outward to positive and negative infinity in the domain. But now the range is going to be from this point down to negative infinity. Make sense? How do we know if there's a negative right there? So it's possible you could have negative infinity to the negative 2. It just depends on whether you have a negative or you have a positive. Do you see how the quadratic and the absolute value are very similar? The positive or the negative is what hinges everything. Here, if you've got a positive, it's going to be this number to infinity. If you have a negative, it's going to be negative infinity up to that number. Well, for the quadratic, again, it all hinges on the vertex. It's either going to be the y value up to infinity, or if there's a negative, negative infinity up to the y value of the vertex. Does that make sense? That's just the nature of the quadratic. Because again, technically, as the graph moves up, gets to that vertex point, it's going to redirect and go back down again. Or if it's going this way, down to that bottom point, but then it'll reverse course and go back up. Okay? Questions on that? All right, next limiting trait. By the way, notice all three of these, you can plug in whatever you want. No limitation on what you plug in for a constant function because there's nothing there. No limitation on what you can plug into an absolute value function. Now, what's it going to do with it? It's going to spit out a positive unless there's a negative in front of the absolute value. Same thing with the quadratic. You can plug in whatever you want, but that x squared is going to make it positive, right? And we'll know based on the vertex where that is. The next two, the domain is up for discussion. So the next limiting trait I want you to write down. It's called a radical function, but I'm just going to say even roots is your next limiting trait. Even roots. The first of these is radical functions. That's their name, but the trait you're looking for, even roots. Why not odd roots? Well, because if you take the odd root of a negative, you get a negative. Take the even root take the odd root of a positive, you get a positive. Odd roots keep whatever signs you had before. Even roots are weird because you can't take the even root of a negative. And also, because that's true, that limits what you plug in and it limits what you get out. Let's take, for instance, this function, f of x equals the square root of x minus 4 plus 5. We alluded to it already. There's a limitation on the domain here. I better plug in at least how big a number for my x. I better at least plug in a 4. Because 4 minus 4 just gives me anything smaller than 4, I'm going to get a negative. You can't have a negative, right? As long as I plug in 4, 5, 6, 7, 8, do you get the idea? At least 4, anything bigger is good too. Does that make sense? Now, how do I determine the domain? Here's the key for the domain. The radicand has to be positive, right? And if the radicand has to be positive, that means greater than or equal to 0. So if you wanted to just think logically, okay, I better at least plug in a 4. That's how I look at it. If you're like, well, I'd rather memorize a rule. I personally hate memorizing rules. But if you'd rather, set x negative 4 greater than or equal to 0. Move the 4 over. X has to be greater than or equal to 4. In other words, 4 to infinity. Okay, that's the mathematical way to solve the domain. Questions on the domain? Well, let's think about the range. This is kind of like the absolute value again, because right now, this thing, because of the understood positive in front class, this thing only spits out values between 0 and infinity. Positive numbers, right? Positive square root only spits out positives, only spits out between 0. It doesn't literally spit, by the way, just use the expression. Anyway, spits out, I'm going to go with that. Spits out 0 to infinity, right? Well, but then we're going to add 5 to whatever this spits out. So if it spits out 0 to infinity, then I'm going to add 5 to all of that. What's my range going to be? 5 to infinity. Since you can't really add 5 to infinity, right? It's already infinity. But 5 to infinity. Or, what if this had been a negative? Well, now what kind of numbers is that radical going to spit out, class? Negative numbers. In other words, it's going to spit out between negative infinity and 0. Okay, well, if you take negative infinity to 0, add 5 to that, what you going to get? Negative infinity to 5. It's going to just shift the whole number line 5 units up, except infinity can't shift, so negative infinity to 5. Again, it depends on whether it's a positive or negative, but notice it's the number that's being tacked on at the end that makes the difference. So if this had been a positive 3, then 3 to infinity, or negative infinity to 3, depending on whether there's a positive or a negative. Notice the domain is unaffected by all of that. The domain, you just got to make sure you at least hit a 0. Make sense? Questions on even roots. All right, last limiting trait is also something we kind of alluded to earlier, and that's fractions. or if you're following along in your book, which I didn't tell you to, but if you were, it would be rational functions, fractions. We're going to talk a lot about fractions a little bit later on. We'll get into more detail. For now, okay, what I'm about to tell you isn't always true, but for now it's going to be true, and then I'll teach you other things later that'll get a little bit more detailed. But for now, fractions, let's think about it. We said f of x is equal to 2x plus 1 over 3x minus 1. Well, the big deal with a fraction, remember, is the denominator cannot equal 0. So if I want to figure out what limitations are on my domain, I just take the denominator, set it on equal to 0 like we did all through section 1.7, and what one thing can x not equal, class? Add 1, divide by 3. 1/3. Good. I can see your lips moving. Good. Move the 1 over. That's a 1. 3x can't be 1. And then divide away the 3. X can't be a third. You plug a 1/3 in there, it's going to give you a 0 in the bottom. Can't have that. So the denominator here is all real numbers except 1/3. I plug anything else in for that fraction. I just can't plug in that one. Now the next one is where things are going to get different later, but for now, the types of fractions we will work with, here's the limitation on the range. Real quick, let me write this down. Denominator can't equal 0. And make sure that's showing up on the screen there for Brecken and Gavin. Okay, denominator just can't equal 0. That's my domain limitation. The range is kind of weird. You cannot equal, or f of x cannot equal the ratio of the leading coefficients. So f of x can't equal the ratio of the leading coefficients. So what you're simply going to do is look at those leading coefficients and say, okay, that's what f of x cannot be. Or y is how we usually think of it, but we're in function notation now. So if you made a ratio 2 to 3, we call that 2/3. Yeah, f of x can't be that. And we'll explain the y's and some things in that, the why, the wherefores, so to speak, later. But for now, you just memorize can't have the ratio of leading coefficients. If it's not one of those 5 things, if it's not a constant function, if you don't see absolute value, you don't see a square for a quadratic function, you don't see a radical, an even root specifically, or you don't see a fraction, it's anything. Plug in whatever you want, get out whatever you want. Make sense? But those 5 things are going to limit our functions. You should be in your books already. Maybe some of you, I guess, have closed them. Maybe I said you could. Turn back to page 186. Turn back to page 186. And let's take a look at some of these functions. Number 1. In your textbooks. Number 1, do I see any limiting traits to function number 1? It's not just a plain constant. It's not absolute value. No quadratic, no squared, right? It's not got an even root. Don't got a fraction. There's no limiting trait. So what's the domain, class? All real numbers. Negative infinity to infinity. How about the range? All real numbers. Negative infinity to infinity. However you want to put it. I'm lazy. I like all real numbers. To me, that's easier than negative infinity to infinity. Look at number 3. We're on page 186.
156.
Okay, 186. Let's see, something looks different about your page. Something's not right there. Okay. All right, page 186. That first one, there's no limiting traits. All real numbers domain, all real numbers range. Look at number 3. Thoughts on the domain? Plug in whatever you want. How about the range? Get out whatever you want. There's no limiting traits. There again, what am I, without looking in your notes, looking up here, without looking in the notes or in the book, what are the 5 limiting traits? Call them out. Constant. Even roots, absolute value.
Fractions.
Quadratic or squared, and then fractions, right? If you don't see any of those, it's going to be anything. Look at number 5. Any limiting traits?
Yes.
What is it? Oh, it's a constant. All right, so what do I do with the domain? Anything I want to plug in, because there's nowhere to plug it in anyway, right? It's like, for instance, if I guess if I stood in front of this outlet right here, and my kid had a power cord in his hands, like, ooh, where do I plug this in? Plug it in wherever you want, kid. nowhere else to plug it in. This is it, okay? There are more in the room. They're just all covered by things at the moment, so you can't get to them. But anyway, but as far as the kid's concerned, there's nowhere to plug it in. So he literally could plug it in anywhere he wanted because there's nothing to do, right? Anything you want. But what will always be the output you get? 15. So the property we write that is bracket 15, comma 15 bracket. You can choose any, you're going to get out all the values between 15 and 15. In other words, 15, right? Look at number 7. Any limiting factors? Once again, it's a, what's the domain? All real numbers. What's the range? -20 to -20 in brackets. Look at number 9. Any limiting factors? Absolute value. Now look at that absolute value. What sign is in front of the absolute value? Positive. That means the absolute value class can only spit out positives. What can you plug in? Anything. So the domain's all real numbers, right? But thinking of the range, it only spits out positives. And then, once you've got something that's only positive, you're going to add 8 to all of them. So picture the number line. You've got all these positives, and you add 8 more. What's that going to do to the range of possible numbers you can get out? It's going to go, instead of 0 to infinity, which is what we call positive numbers, it's going to go 8 to infinity. Does that make sense? Again, I can memorize rules, or I can think practically, logically through it. I want you to get to the point where you're not memorizing, but thinking. Does that make sense? Because I hate memorizing rules. That's annoying. Okay, so trying to help you to understand it. Look at the next one, number 11. Again, the limiting factor here is absolute value. But I can plug in anything, whatever I want, all real numbers. However, what sign is in front of that absolute value on number 11? Positive, which means it only spits out positives, which is 0 to infinity. But then what do I do to all those numbers? Subtract 10. So what's my possible range of values? -10 to infinity. Does that make sense? Do you see how to logically think that through? Look at number 13. Once again, what's our limiting factor? Absolute value. But looking for, okay, once again, domain, anything you want, right? You can plug in whatever you want into the absolute value, but it's only going to spit out what kind of numbers? Negatives, which means negative infinity up to 0, right? Then what do we do with our negative infinity up to 0? We add 4. All right, so now where are we? Negative infinity up to 4. Does that make sense? Picturing number lines as we're doing it will, I think, help you. Number 15. What's the limiting factor here? It's quadratic. And what shape is a quadratic going to give us, class? Parabola. Say that with me. Parabola. It's not on the board anymore. It's spelled parabola, like Ebola, but para, which means alongside. So this is alongside the bola. All right? Parabola. Okay? Emphasis on the second syllable. Parabola. Say that with me.
Parabola.
Parabola. Parabola just means this shape or this shape. So what do we call the point of the parabola, class? The vertex. And either I'm going to go from vertex up to infinity or negative infinity up to vertex. How do I know whether it's a U or an N? Looking at the equation, how do I tell if it's a U upright parabola or an N or a down parabola? All depends on the x squared. If it's positive, it goes up. And if it's negative, it goes down. Does that make sense? So looking at number 15, does it go up or down? It goes up. Now, which value, I know they're the same on this particular vertex, but which value am I focused on, the x or the y? I'm focused on the y because I'm thinking of the range here. How high can it go or how low can it go, right? That's range. That's f of x values or y values. The domain on a quadratic is anything. Plug in whatever you want into the quadratic, right? But what's the quadratic going to do to it? It's going to bend it into a parabola. So for number 15, the lowest my value can be is -4, specifically the y value. And then it goes up to infinity. So we'll say -4 to infinity. Does that make sense? For the range. Look at number 17. What's the domain? Anything. Quadratic, you plug in anything you want. But it's only going to spit out as small a value as the vertex's y value. So in this case, the smallest you can get is a 4, and then it's going to go up to infinity. So 4 with a bracket to infinity with parentheses. Do we see how those two are very similar? All right, look at the next page. Notice what they did differently with our quadratic, though. On number 19. Thoughts? There's a negative, Kendall. Good. Negative in front of that x squared, which means now the parabola flips down. So the highest it can be is the y value of the vertex. So the biggest you can get out, you can plug in anything. Domain is still all real numbers. But the biggest number you're going to get out of that function, the range biggest value is 24. It's actually going to start way down, class, at negative infinity, come up to the 24, and then go right back down again. So negative infinity to 24. Does that make sense? I can bracket on the 24. Questions on quadratics. Let's look at absolute or radical functions, the even roots. Looking at 21, you see the radical. You got to be careful, because now for the first time you can't plug in whatever you want. You can only plug in at least an 8. As long as you plug in at least an 8, 9, 10, 11, 12, it doesn't matter. But at smallest number you can plug in, there's an 8. Does that make sense? So how would we describe the domain on 21? 8 to infinity. Does that make sense on 21? As long as you plug in at least an 8, we're okay. You go any smaller than 8, you go get a negative. You can't have a negative not inside the radical. Make it sense? Now, let's suppose you plug in for your domain something between 8 and infinity. Still, on number 8, that radical value is going to spit out, that means range, what kind of numbers? It's only going to spit out negatives. How can we describe negatives? Negative infinity up to 0, right? But then what do we do with this negative infinity to 0 that the radical gives us? We add 1 to it. So now my range is negative infinity to 1. Does that make sense? Look at 23. I better at least plug in a 1. Or bigger. So here the domain is 1 to infinity. But what's that radical going to spit out, class? Positives, meaning 0 to infinity. But then what do I do with my 0 to infinity? Add 4 more. So now I'm at 4 to infinity for my range. Is that making sense? We still keeping up with me? Number 25. What's the magic number in the radical? A positive 3, because it says negative x. If I plug in a 3, I'm good, right? What about a 4? No. 5, 6, 7, no. But I can go smaller. In this case, not the smallest I can plug in, class, but the biggest I can plug in is a 3, because the x itself is negative. So again, if you wanted to set the radicand greater than or equal to 0, negative x plus 3 is greater than or equal to 0, well, I'll just move the x over as a positive and get that x has to be less than or equal to 3. Again, I think it's logical to look at it and say, well, I can't plug in bigger than a 3, but like 2, 1, 0, any negatives are fine, right? Because negative times negative gives you the positive. So negatives are good. So here, the domain goes from negative infinity up to the 3. As far as what I'm allowed to plug in for that x. Does that make sense? But what's the radical going to spit out on 25? Only positives. Because in front of the radical on 25 is a positive. Understood, but it's a positive. Which means 0 to infinity. But then what do I do? Subtract 13. So now what is it? Negative 13 to infinity. Does that make sense? On what you plug in, get out, that kind of thing. Number 27. What's the smallest I can plug in? Negative 5. Negative 6 would be too small, but negative 5, negative 4, negative 3, 2, all positives, they're all good, right? So negative 5 to infinity is my domain values I plug in. Number 27, what's the range? Right, it would have been 0 to infinity, but I subtracted 6. So negative 6 to infinity. Stay with me through the bell. Number 29. What's the smallest value I can plug in on 29? I heard it from Maddie first. A negative 5, right? It's the smallest you can plug in. So you can go from negative 5 to infinity, right? But what's it going to spit out? It's going to spit out negatives, right? And then we subtract 15 from that. So what's my range? Right, not negative infinity to 0, we have to subtract 15. Negative infinity up to negative 15 is my range. Very quickly, number 31. What's the only thing x cannot equal? Negative 3. It's all real except negative 3. Stay with me. What about values that you can get out? Remember, the only thing you cannot get out for f of x is a ratio of the leading coefficients. What are the leading coefficients in number 31? 1 and 1. So what can I not get out? There's no way to get a 1. You can't plug in a negative 3 and you can't get out a 1. Other than that, you can plug in anything you want, get out anything you want. 33. What's the one value you cannot plug into 33? A 1. Because that would give you a 0 denominator. You can't have that. What's the one number you'll never get out of 33? A 2. Number 35. What's the one thing you cannot plug in? 3. The one number you cannot get out? 5. Number 37 is a fun one. What's the one thing you can't plug in? 10 thirds. Remember, set it on equal to 0. What's the one number you can't get out?
1.
A 1. And last one, number 39. What's the one number you cannot plug in? Negative 3 halves. What's the one number you can't get out? A 6. All right, now, let me say this. If you felt like you kept up well, good. Okay? If you felt like, I was a little confused, it might be worth tonight going back and rewatching the video. Okay? It's on YouTube. That said, for homework tonight, you're going to do all the even teal problems. Pages 186 to 187, the even teal problems. Page 186 to 187, 2 through 38, the even teal. Not all the even, only the teal even problems. Make sense? We are looking at a quiz tomorrow. This is not on it. So tomorrow, when I say clear your desk except for 2 sheets of paper and a pencil, this is not on it, okay? Variation, the stuff that you had in the homework last night or over the weekend, we're going to review that a little bit tomorrow and take the quiz over that. This is not on the quiz, so don't panic and shut your brain down when I say to clear your desk. You're good on variation, you're good on function notation. This stuff we're going to work on a little more, okay? Any questions before we dismiss? All right. Well, you are dismissed. Have a wonderful rest of your day.